All right, so we're talking about the electrolysis of water. We've been doing electrolytic cells for a little bit, so this should make some more understanding of this. But the point is, we're going to break water into two components. What have we done so far? We've taken molten. In lab, we take copper chloride. We took 2 electrons in. We forced the charge on these electrons, and we made pure copper at 1 electrode and pure what? Chlorine gas. We're making the elemental forms. So the one thing you think about electrolysis is we're going forward to produce what? Break something apart into its usual elemental stages. For instance, we had copper chloride in lab, maybe. Okay, hold on. I want to write on. My bad. Give me a second. Okay, so it's going to give me that. Good beans. So what we had is in lab, we had copper chloride, copper 2 chloride, and let's go a little thicker here. So we had copper chloride, copper 2 chloride, and by adding energy, we made pure copper and pure chlorine. And we know chlorine is Cl2, and I put the zeros above. Okay? And we call this a decomposition reaction. And the point I'm trying to make with electrolysis is we're taking an ionic compound. We did it aqueous. Normally we did it with what? Molten to eliminate a problem. Now when we did this lab, did anyone notice what was happening at the electrodes in this lab? We know there was fizzing occurring to make the chlorine gas, correct? And then we noticed there was copper being made. That's what's drying in the oven right now. But did anyone notice there was fizzing on both electrodes? Yes. So we had a side reaction. Because we did this in aqueous environment, we were actually doing this experiment as well. Okay, it's important to realize that. If we had melted molten copper chloride, then that would not be the case. But because I had aqueous, I had water present next to these electrodes, we were oxidizing and reducing water. So I want to talk about this experiment, all right, and understand that we're still making the pure forms, no matter what. And the reason for that, this is really important, electrolysis is really important in the history of chemistry because this is the first place we purified, okay, non-gases. For instance, you should know that copper that comes out of the ground comes as copper oxide. Aluminum that comes out of the ground is aluminum oxide. What are they? What are they? They're salts. What are ores? They're three-dimensional Al+3 oxides. They're ores. They're what? They're the reacted forms of the metals. They sit in the presence of oxygen. They lose their electrons. Okay, oxygen becomes -2. Iron becomes +2, and they stick together to make a crystalline ionic structure that's different than the original metal. We want to use these metals, so we want to purify them. And that's how we made the pure copper. That's, of course, how they purify aluminum by electrolysis. We call it smelting for iron. The first, and I'll talk about this, the first column on the periodic table is the what? Alkali metals. If I were to drop pure sodium in water, it explodes. How do I have pure sodium? How do I have pure potassium? Because we do electrolysis. Those metals are never found in nature, the first alkali metals. They're never found in nature because they're so reactive, what? They'll explode in water, so we only find the reacted forms of them. So understand electrolysis is used to purify, and we're going to get to pure forms of water. What are the pure forms of water? What does water break apart into? It's made of what? Hydrogen gas and oxygen gas, and that's where we're going to make it the electrodes, the pure form. And it's going to take energy because water is very stable. Okay, let's talk about the basics here. Okay, so let's label our battery or our battery voltaic cell. Okay, first step. Okay, we've got our voltaic cell here. Let's just go write it. It's also, you can say, galvanic cell. It's our battery, and if we're cool, we say bat, right? Okay, voltaic cell. It's our DC current. It's our power supply. There is no electrolytic type of diagram that's not going to have a power supply because, as you notice, it's not on, there's nothing happening. This is non-spontaneous. Now, just by convention, our black lead is going to be our anode. And what charge, by convention, do we give the anode? This is the battery that produces the electrons. Negative. Or should I say positive that it's negative? You're right. Sorry. Okay. The red lead is going to be the what?
Cathode.
The cathode. And we, by convention, we give the cathode what? A positive. Cool beans and beans and chill. Now, what do we know? The anode of the battery pushes charge. It oxidizes. So the black lead is going to send electrons, anode, to the what?
Cathode.
Yeah. So this lead is connected to a brass fitting that's connected to this electrode. And right here you have a platinum metal sticking out. So right here, this right here is going to be our, and someone said it, the cathode. All right, so let's write it. So I'm going to write it up here to keep things clear. Electrons always flow from what? Anode to cathode. We're pumping electrons. So this little tip, this platinum tip, is going to be negatively charged because we're pumping electrons to it. And of course, what's the charge of the cathode if it's connected to the negative anode? Negative in the electrolytic cell. And we learned that I could have done what? Couldn't I just switch this over here? Couldn't I made this the anode? Yeah, we decide who the anode and cathode is by how we connect it to the battery. The battery makes it happen. Okay, that being said, cathode's positive, so it makes this what? Positive. And what is this? If this is the cathode electrolytic cell, this must be the anode. And electrons clearly flow from what? Always from the anode to the cathode. So electrons are being forced back. Okay? And they go around and around they go. They're forced back to the cathode of the battery. Cathode is still pulling charge. The anode is still pushing. And that push and pull of energy across the circuit is making this have the energy to occur in front of our eyes that normally wouldn't. You turn off the battery, it stops. Right now, it's not. Now, let's predict what's going to happen. We now know that in electrolysis, we're making the pure forms. But which one am I going to make hydrogen? Which one? Where is there reduction oxidation? Well, I'm going to first start here. Anode and cathode. So there's where I'm going to start my business. Let's look at the cathode. What's going to happen at the cathode? Red cat, right? So we're going to do reduction, which means what? Reduction means gaining electrons. So let's take water, make some room because we're going to rewrite this a couple times. Water is going to gain some number of electrons, and it's going to become something. And again, give yourself some space. We might have to rewrite that. Let's think about water for a second. I have some space over here to make some sense of it. Okay, so we know that water looks like this. Very, very attractive element that loves electrons, oxygen. It has 6 outermost electrons. And hydrogen it bonds with has 1. The shape of it we'll get to another time. But right now, hydrogen brings 1 electron to the table. It's got 1 valence. And so does this one. And the reason why we have this formula is because oxygen has 6, each H brings 1, and by sharing, because they're both pulling, they covalence to make 2 covalent bonds. Okay, party people, what am I getting at? Okay, well, looking at water, notice the H's. Notice something about the H's. They're a little farther away than their electrons. What happened to their electrons? They were being pulled in by the oxygen, because when you compare oxygen's ability to pull on electrons, we call that electronegativity. It is a higher amount than the hydrogen. So the oxygen's winning by pulling that pair closer. And as we learned in AP Bio, this makes these hydrogens electron deficient. Think about it. What is hydrogen? 1 proton, 1 electron. You pull its electron farther away, what's left? A little proton. So little protons are dangling. And if you're tiny, Coulomb's law, small distance, your force of attraction's high. So these things are pretty darn positive out here. They kind of have had their electrons pulled away. So, party people, I know it's not funny, but I'm just guessing. Okay? Who do you think is going to grab the electrons if I force them on high enough? Who has the ability to accept electrons? More so than any other part of the water molecule? The hydrogens. So, what's going to happen is we're going to force electrons onto the hydrogen. Remember, hydrogen holds one electron, it's got one proton. So I know it's got one kind of pulled away, but if we force it on the hydrogen, boom, hydrogen's going to say, thank you very much, and I'm going to be elemental hydrogen with one electron. Do we see hydrogen ever like this in the environment? No, we see it as what? So, party people, we're going to make H2. Now, some people say, well, that must mean that we pull another, right? But wait a minute. Once I lose a proton, what's left? What's left here? What is this right here? OH what? Negative. Right, you lost a positive. That's a hydroxide ion. Hydroxide ions are stable. Don't we make precipitates and things with them? And guess what? The whole thing is -1 charged. This H was dangling water as +1. If the whole thing remaining now is -1, that H isn't available to what? Accept another electron. Because it feels the -1 across that. Isn't H a proton? You pull out a +1. This remaining is a hydroxide. So what are we going to make? OH minuses. Oh, wait a minute. We make one OH minus for one H plus, but we know that H2 comes together. Don't I have to do this twice? Right. You see the chemistry. Now, I'm not just telling you. You're understanding. That's what I want from you guys. So 2 of these absorbs how many electrons to get 2 H2s? That has yeah, you need 2 of them. And you're going to produce how many hydroxides? 2. And an H2 molecule. That's water getting reduced. And you can see it, feel it, understand it, not just say, well, there's the reaction. I want that for you. Okay. Now, that is the reduction half reaction. Now, party people, and people that want to go to the party, we can go to where? Right in the middle. So water, 2 waters gaining 2 electrons makes hydrogen and 2 hydroxides. And you understand it. What's the value? What's the number? -0.83. Write it down. What's that mean? You need to add that. Yeah, correct. Add that value to make it happen. Water is stable. It doesn't break apart without you forcing it. It's a good thing, right? Doesn't the plant need to take water and combine it with the CO2 to make the glucose? And photosynthesis. It better get to the plant. It better be stable. Oh, think of it this way. What about combustion when I burn something? Isn't water stable? Isn't the thing I'm burning unstable? It's the reason why things go in nature that way. Okay, cool beans and beans are chilled. Now let's go back to the other one. Let's explain oxidation of water, because I want you to understand it, not just tell you about it. So, let's go to the next one. Okay, so let's go to, where do we go? Yeah, I gotta erase, make some room. Okay, so what's going to happen at the anode? What's going to happen here is what? Oxidation. Christmas in July. And here we go. So we're going to take water, and it's going to do what? Give off electrons, right? I don't know how many yet. You with me? Mm-hmm. Okay. Now let's talk about water a little bit here. I'm going to do it again. You have O. We have these tightly held electrons with the O here. And then we have these electrons here. And we have an H, another H, and an electron from the H. Okay, I didn't draw it very well, but, okay, does everyone understand that because these electrons here do not have a positive nucleus pulling on them, that they'll be held tighter? Remember, what's a chemical bond? A covalent bond. I'm a nucleus. Val's a nucleus standing here. And our nuclei are simultaneously attracting electrons. That's how it works. And if we attract our electrons and fill our outermost electrons, it's a bond. Remember, oxygen has 6 valence. 2 more electrons that H is given, it feels like it has 8. So party people, these electrons are held more tightly. It is these electrons that are still pulled toward the oxygen, but not pulled as what? As much. So those electrons are the ones that if we're looking to oxidize and force oxidation to occur, it is the electrons here, okay, that can be what? Ripped away. And they have to be ripped away because they're still being held tightly by the oxygen. Okay, so the anode is going to be forced to give up its electrons to the cathode. The cathode is yanking. Now what electrons does it yank? It's going to yank these. Now in truth, it's going to yank one of these. And that electron goes this way. Now, if we yank that electron, okay, remember, hydrogen kind of brought one to the table. So you kind of pulled an electron away from the H. So the H is going to kick out to be an H plus here. Now you can also think, another way to think, is that 2 of these electrons are yanked. So these 2 electrons in the water get yanked away. I'm going to put a 2 here. That means hydrogen no longer what? Has any electrons, if you want to think that way. We don't know. No one's looked at it that closely. You can't see electrons. Okay? But through tests, it's either one or the other. But the bottom line is, these electrons have been pulled away, and now you're left with what? An H without any electrons. And it's an H plus. So we're going to make what? H plus. Now, party people, what's left? I'm left with an O with 1, 2, 3, 4, 5, and 6. Does oxygen exist as an element by itself? No, it's a diatomic element, the Hofbrinkel. So what are we going to make? O2, so another O with 1, 2, 3, 4, 5, 6. And party people, by sharing, this oxygen feels like it has 8. This guy, by the way, it's a double bond there. We'll learn about that. So you're going to make what? What are we going to make? We're going to make O2. You with me? But in order to do that, I need to have an O from how many waters? 2. 2. And we're going to lose, each water loses a what? We're going to have to lose 2 H's, correct?
Oh, yeah.
So 2 waters, that's going to be what? 4 of these. How many electrons are involved? 4. To make a what? An O2. And party people, okay, let's go find that half reaction. I know it's going to come back now. Okay. So we go here. And let's go here. Maybe. And let's go up. And let's go find, now you notice how far up water is. So we're going to go find the oxidation. Now the best the metals that oxidizes are lower what? Bottom right? Where's water? It doesn't like to oxidize. A little bit lower than what? Gold. Water doesn't oxidize really well. You can't force electrons. Can anyone understand why? Oxygen loves what? Pulling on them. So you're going to need what kind? What's the energy for it to oxidize? Negative 1.23. Okay? I'm going to keep going and finish. So let's finish this up. All right? And I'll give you a break once we finish this up because of the technical difficulties. So back to here. Crossing our fingers. Okay. Now, what was the value for this? Negative 1.23 volts. You have a unit. What was the value here? Negative 0.83. Okay. So what's going to be bubbling at the cathode? What am I making? Hydrogen gas. So bubbles of joy. We're going to be making H2 gas here. What's going to be made at this anode? O2 gas is made here. And we'll see bubbling going on. So when you saw fizzing in your lab, at the anode, what were you making? Oxygen gas. You couldn't help it because we were dealing with what? An aqueous environment. Is it occurring now? No, because I have yet to turn it on, so let me turn it on. All right? Okay, we got this on. I know it's hard to see, but you can see the fizzing going on. In fact, I'll make this bigger, okay, because I'm going to show off here. Now I know how to use this. So here, let's go Christmas. And you can see an aggressive fizziness going on here. This is a lot more fizziness than here. Why? Anyone know? Anyone make a guess? It appears to me there's a lot more bubbles of H2 than bubbles of O2. You're onto something. You're right.
There's double the amount of hydrogen gas as oxygen.
Right, there's H2O. There are 2 hydrogen atoms per 1 oxygen atom in water. This experiment proves that it's H2O. Now, they didn't know this when they ran this experiment in the late 1700s and 1800s. They didn't know what to think of it. It was a phenomenon. Until you have mole concept, you can get that. Now, party people, let's get out of this. Okay? Now, you're going to see this in a second as this runs. What's happening here, if you didn't notice something, we're doing water by displacement. I'm going to show you what I mean. Okay? I had these tubes pre-filled with water. I'm going to show you how this is. They're collecting a gas by water displacement. So party people, what we did is this. We took a tube. This is the tube, right? I'm thankful that I had enough to fill that up. Okay. Now, what I'm going to do is I'm going to cover it, invert it into this water. I got some bubblage. And then if you notice, the water didn't fall out. There's a little bit of bubble there, Bad Grodsky. And the reason why the water is staying in there is atmospheric pressure. The gases in the air are doing what? Slamming down on this, keeping the water. We can actually support 33 feet of water in any side tube. Okay, it's a barometer. We'll talk more about that. But I started this way. Now, as gas is being made, what's happening? As gas is being collected, it goes up here and pushes the water out. We're collecting gas by water displacement. The gas is less dense, it rises to the surface, and it pushes the water out. Okay? And that's what's happening. Can anyone look to see at the top of the tubes anything also proving the 2-to-1 ratio? Look at the top of the tubes here. I know it's subtle, so I'll make it become more clear for you. Of course, that stuff's in the way. That didn't work out as aggressively as I wanted to. Can you see there's twice the volume as here? Now, we haven't gotten there. They didn't know what to do with that. Avogadro's hypothesis, we'll talk about it. He fixed all this. They didn't know what to do with this. They always knew that, hey, if I'm making hydrogen, there's twice as much volume of gas being collected. Big deal. Well, think about it. If gas molecules are on the top of this being made, aren't they flying around? Aren't they pushing the liquid down? When the gas gets to the top, it's pushing the liquid down. If you've got more hydrogen molecules here than here, is it going to make twice the space? That's what the key was. But forever people thought that there was in water one H to one O. They thought water was a hoe. This experiment, they didn't know how to handle it, was proving that water was H2O. Bottom line is, producing twice the amount of hydrogen as oxygen. Now, really could have, like, okay, Mr. Grazi, great, cool, but wait a minute. Fuel cells. Ever hear of fuel cells? Fuel cells are the idea that we take water into our car, charge up the battery, like you would a Prius or a Tesla, although they don't use fuel cells. And from the battery, you put electrodes in water, and you produce what? Hydrogen and oxygen. Is this non-spontaneous? Yes. Very non-spontaneous. Does anyone know how spontaneous H2 with O is? Very. It explodes, and I'll explode that next week. In fact, the reaction between twice as much hydrogen to oxygen is so exothermic, is so spontaneous, that's the reaction that actually lifts the space shuttle, although we don't use it anymore, into orbit. That's the same reaction. It's explosive. So I have the correct explosive ratio here. So the idea is I can run a car by taking water, sticking electrodes in, with a battery, of course, and making the fuel that explodes in my internal combustion engine with the right ratio that moves the car. That's how a fuel cell works. Okay, and that's, of course, electrolysis of water. It's got important implications. Hope that works.